Okay. Hi, everyone. My name is Hai. I'm from Washington University in St. Louis. Today, I'm going to present our work, Self-Learning of Lifted Action Model. The other author are Professor Juba from Washington University in St. Louis and Professor Stern from Palo Alto Research Center. So the problem that I'm trying to solve is called the safe model-free planning problem. Before I explain what it is, I want to recall the classical domain independent planning problem. In a classical domain independent planning problem, a domain's model is a model of the environment and how the acting agent interact with it. If we know the description of the domain, we then can use any AI planner to generate the plan and given the initial and the goal state. However, in general, creating a domains model is a very hard task. So how do we overcome that problem? A popular approach is to use learning. So we learn the action model through a bunch of trajectory that can be obtained by a human operator. However, this approach does not guarantee safety. So sometimes the action may fail, but in many problems, that failure is not acceptable. For example, the robot may not go to a dead state. And in that problem, we only allow to do a safe action. So for those domain, we need to generate a plan that is guaranteed to be successful. In other words, we need to learn a safe action model. So that problem is called the safe model-free problem, and it is the main focus of this work. So you may want to wonder, what does an action model look like? For a strip-line planning domain, an action model gonna consist of a precondition, which is basically when you can do an action X, and effect, which is what does an action X do. So for the set action model, you are only allowed to do action X if you are sure it can be done, and you are only allowed to do action X if you know what its effect will be. There are existing work on learning the action model. For example, we have Pharma by Aineto et al. We have ARM by Yang et al. And Lockcom by Creswell et al. However, this work does not guarantee safety. And for the safe model-free planning problem, there also existing work by Dr. Stern and Dr. Juba in 2017. However, the work is limited to grounded domain, which doesn't generalize well to different set of objects. So in this work, we want to solve the problem of learning the lifted domain, which is more compact and generalized across different set of objects. So let's first look at an example of a logistic domain. Suppose we have 5 objects, a truck, a packet, and 3 locations ABC. A lifted literal is basically a relation over a list of types. So for example, we have the lifted literal SXY, which are representing if a truck X is at location Y. And meanwhile, a grounded literal is basically a pair of lifted literal and object binding. The binding is basically a mapping of the parameter of the lifted literal to a set of objects. So in this example, the grounded literal truck A is basically a pair of the lifted literal SXY and the mapping that X to be a truck and Y to be the location A. Similarly, we have the lifted action and grounded action defined in a similar fashion. So from the definition, we can see that the number of grounded action for a lifted action can grow polynomial with the number of the domain's object. For example, with the just a move action, it can do like six grounded action. So the question is now how to learn a lifted representation of a model. So we can, although the action model is given by lifted literal, but we observe that the chains are given in terms of the grounded literal. So we see that we can infer the lifted literal for the action model from grounded literal. that appear in the chase using the two following assumptions. The first is that all the precondition and effect are bound to action parameter. The second assumption, we call it the injective binding assumption, is the binding are unique. So the same object is not bound to two different parameters of the same action. So here are the main contributions of our work. So first, we propose a safe action model learning algorithm that can probably learn safe lifted action model. We call it the SAM learning algorithm. We then provide a proof of approximate completeness of our SAM learning algorithm that is with high probability over distribution of goal. The action model produced by our SAM learning algorithm has a plan that can achieve the goal. And then finally, we have experiment on IPC domain that's so fast learning of our SAM learning algorithm. So first, let's look at how we learn the safe action model. So here are the three inference rules that we observe. The first rule is that the bioliteral that do not appear in the pre-state cannot be the binding of the listed literal in the precondition. The second rule is that the bioliteral that do not appear in the post-state cannot be the binding of the listed literal in the effect of the action. And the third rule is the bioliteral that appear in the different of the pre-state and the post-state must be the binding of the listed literal in the effect of the action. So with the inference rule, we come up with our SAM learning algorithm. So for each action A, we first initialize the precondition of A to be own parameter bound literal. We also initialize the effect of A to be an empty set. And then for each state action chiplet in the X trajectory, we update the precondition and effect of A using the three inference rules mentioned above. And then finally, after we go through all the chiplet in X trajectory, we return the resulting action model. So here, let's look at to understand how our SAM learning algorithm works. Let's look at a simple example of how we use SAM learning to learn a lifted action. So go back to the logistic domain that I mentioned above. Here we want to learn the move XYZ action where X is an object and YZ are the location. Here we observe a state action, pre-state action and post-state chiplet that move the chuck from A to B. On the left, we have the grounded literal that we observe for the pre-state, and on the right, we have the grounded literal we observe for the post-state. So initially, we have the precondition can be on parameter bound literal. So we have it can be at XY, not at XY, at XZ, not at XZ, and the effect is empty. However, using the rule that the three inference rule that I mentioned above, after we observe that state action chiplet, the precondition is now at XY and not at XZ, because not at XY and at XZ is not in the pre-state. And similarly for the effect, as I mentioned in the three inference rule, the difference between the pre-state and the post-state is the effect of the action. So we observe only the difference here, the struct A to switch to struct B and not struct B switch to not struct A. So that we conclude that the effect of that action after observing that state action chiplet is at XZ and not at XY. Next, for the theoretical guarantee of our algorithm, we prove that our SAM learning return the strongest possible safe action model. We also prove that planning with safe action model is sound. And then finally, we give a proof of approximate completeness of our SAM learning algorithm. So given a number of trajectory, for example, draw from a distribution that is linear in the size of the domain, we obtain an action model with high probability that is there is a successful plan using the model returned by our SAM learning algorithm. So next we have the experiment on the IPC domain that satisfy the injective binding assumption that I mentioned above. For each domain, we generate the problem and solve them using a planner to obtain the trajectory, and we use that trajectory to learn the action model. The baseline that we compare is Pharma by Aineto et al. So here are the domains that we use in our experiment. You can see that the maximum grounded action for a single action are extremely large, and the grounded algorithm will need to see X ground action before it may be used in a plan. So the number of ground action is a lower bound on the number of triplets that needed to learn the action model for the grounded algorithm. However, so here's our result for our using our SAM learning algorithm compared to the Pharma algorithm. We observe that our SAM learning algorithm can learn the action model using the same or fewer state action triplets than Pharma. And also our SAM learning algorithm is resistant to the domain's parameter growth. Also, we note that the Pharma output may not be safe. So in conclusion, for our work, we propose a SAM learning algorithm that can learn the lifted action model. We also prove that the number of trajectory needed is linear in the size of the domain's model, and it does not depend on the number of the problem object. And also we provide experiment on some IPC domain. For future work, we want to extend our SAM learning to harder domain, such, for example, domain with stochasticity or partial observability. That conclude my presentation. Thank you all for your attention.